feel the need for speed. Ow!
All right, so let's briefly rehash what we finished off with last time in class, and that is the idea that kinetics studies the rate of reactions. So for any generic reaction, like what I've written here, we can express a rate law as the rate is equivalent to a rate constant K, and the concentrations of the reactants, here written as A and B, raised to their reaction orders. Now that does not necessarily have to match the balanced equation. Frequently it will not. That gives us some additional information. If it doesn't, it means that the reaction is a little more complex than one step. But we'll talk more about that when we get to mechanisms a little later in the chapter. But just keep your eye on that. If those exponents do not match the balanced equation, something is going on and we're not seeing all of it. Concentrations for this type of problem are always given in molarity terms, and we'll sometimes discuss reaction order as the sum of the individuals as the overall order of the reaction. We'll come back to that in just a little while. All right, so let's look at a realistic example. If we have an equation like what I have here, we have two different reactants, we have three different products. We're not really concerned with the products. They don't interfere with the rate for the moment, but this is a 2-to-2 ratio, so if the rate law follows the balanced equation, we would expect those reaction orders eventually to be 2. So the rate law can be expressed the way we see it here, which is the rate is equal to K times reactant 1 raised to its reaction order, which we'll leave as a variable for the moment, X, and reactant 2 raised to its own reaction order, which we'll also leave as a variable for the moment, which is Y. Now, you'll notice as we start to look at the data that we have original concentrations here. That's what the subscript 0 means after those brackets. Those brackets denote molarity, but that means at the start of the reaction, and you'll notice that the rate will be given as an initial rate. This is very simple to think about. This is when the reaction is at its fastest, when there's the most of those reactants present. So when we talk about rate, that's what the term is that we refer to for the moment, and that is that we're talking about initially, when it's at its fastest, when those concentrations are at their highest. As the reaction goes on, there's less of them, the reaction will have to slow down. What you'll notice, though, is that we have a bit of a problem here. If we put the data from one trial into the rate equation, we're looking at an equation with three separate variables. We have K, we have the reaction order for ClO2, which is X, we have the reaction order for hydroxide. There's no way to solve a single equation for three variables. It's impossible. So how do we get around this problem? Well, you'll notice when you do kinetics trials in the laboratory or when you look at them as problems in a chapter, there's always more than one. It's the only way we can deal with multivariable equations is to have multiple trials to help us eliminate some of the variables. So that's exactly what we're going to do. We're going to try to hold one concentration constant. As you can see here in trials 1 and 2, the hydroxide concentration doesn't change. If we put those into the rate law in separate equations and then treat those as a ratio, we can get rid of some of the variables. So if we do that, we could treat these as an actual ratio. So we basically just divide one set of data by the other, and we end up with a set where we can get rid of the rate constant, which does not change unless the temperature changes. So the assumption in all of this is a constant temperature. And if you notice on the right, we have the same concentration for hydroxide. Even though we don't know what Y is, it doesn't matter. Whatever it is, the same number raised to an exponent over that number raised to the same exponent is 1. So 2 to the second over 2 to the second is 1. 5 to the fifth over 5 to the fifth is 1. Does not matter what Y is as long as that concentration was constant. So we're left now with this ratio getting rid of two of our variables, leaving us only with X. If we simplify that down by canceling out everything, we end up with only that one variable, but we have a bit of a problem. And that is that we still have kind of an odd layout. We don't have an easy way to solve for X here. So we have to kind of pull a little trick out of our math toolbox, and that is carrying exponents through. What we can do with that top number, since it's a direct ratio of the lower one, it's exactly double the lower one, is we can actually separate that on the inside, and then we can pull that 2 out as 2, but the exponent has to carry through both. So we end up with 2 to the x times 0.0500 to the x, and that will cancel out with the 1 on the bottom. So we end up in this case after canceling that out with 2 to the x equals 4. Now hopefully that doesn't require a lot of mental effort on your part to get to x equals 2 from that, but sometimes the numbers are not quite even numbers, sometimes they're triple, sometimes they're quadruple, so it's nice to know exactly how to solve for it if it wasn't quite so visibly obvious. Here's how you do it. You actually take a logarithm of both sides. When you do that, the exponent on the 2 becomes a multiplier in front of the log sign. So that we end up with the log of 4 equals x times the log of 2. We can then do the calculator work and we end up with x equals 2. Surprise, surprise. But that's mathematically how you do it if you needed to and it wasn't quite so obvious. We're going to use exactly the same procedure to solve for y. I'm not going to write it all out for you, but you can see if you look at trials 2 and 3 that the ClO2 concentration is constant, the hydroxide concentration doubles. So we work out the math, we end up with 2 to the y is 2. So in this case, we solve that, we end up with y is 1. Now, notice what I said earlier. That does not match the balanced equation. That tells us, 1, reminds us that we shouldn't trust the balanced equation to give us those reaction orders, ever. 2, it tells us mechanistically later when we talk about what that means, that there have to be multiple steps here because you have more molecules in the balanced equation than you can account for in the slow step, which is what we're really talking about in rate, which is the slow part. The slow part involves 3 molecules. The balanced equation has 4 reactant molecules. So there's got to be another step. Something has to involve that last one. With all of the reaction orders in place, we can then finally solve for K. In a question for the exam, questions from the textbook, you're generally only going to take one of the examples and solve it all the way through because now you only have one variable left. You can use any one trial. In a lab setting where you're doing this, you would solve for K for every trial and average the number. So when you perform an experiment like this in the laboratory, you would do a lot of solutions for K and average them just to get the errors out of it. Well, now that we've dealt with the reaction orders, X and Y in this case, and K, we can finally express what is called the complete rate law. And that is the original rate equation we had with no variables left in it. From that, we can interpret changes in concentration and what their effect will be on rate within a very limited range. We cannot go doing things 100 times more concentrated and expecting it to follow the same rules. We'll talk a little bit more about that when we get to the integrated rate laws in the